Generics. Generics, or C#'s version of C++ templates, provide reusability, type safety, and performance. A typical use of generics is for type-safe collections. As a matter of fact, there are several tens of collections that have been built into the system.collections.generic namespace. Generics can be applied to classes, interfaces, methods, or delegates. Generics provide the means for developing objects and routines with specific functionality while leaving underlying types undefined. Placeholders such as T, U, and V are typically used when the generic is defined and replaced with a real type during implementation. A generic method is a method that operates on variables of types not defined when you design the generic method. The caller to the method will define those types at the time the function needs to be performed. The swap function below demonstrates this. Basically speaking, a swap function accepts two variables and swaps their contents. Since we have to swap their contents at a permanent level, we will pass these variables in by reference. Notice here the data type for the parameters being passed to the swap function are T. Well, as we know, there is no data type in C# called T. T, however, has been defined inside the angle braces where swap is declared. So you can see swap of type T, where LHS and RHS are both going to be of that data type. Then in the implementation of the function, you can see T is a data type. We're using it as a data type here, and we'll call the variable temp is equal to LHS for left-hand side. Then LHS is equal to RHS for right-hand side, and then RHS equals temp. So as you can see here, we created a temporary variable and then assigned to that temporary variable what was the left-hand parameter. Then we changed the left-hand parameter to be what was passed in on the right-hand side, and then we set the right-hand parameter to what temp is. That effectively swaps LHS and RHS. Again, notice that we nowhere in here defined the actual type of data that we're going to swap. So you can imagine we might swap integers, we might swap longs, we might swap strings. So in fact, all of those data types could be used by the swap function. So we don't have to write a specific version of swap for every possible data type. Look in the sample next to that where we declare integers a and b and set them equal to 1 and 2 respectively. We output a and b, so you can see that on the far right, a equals 1, b equals 2. Then we call the swap function, and then we put in the angle braces int, and we pass by reference both a and b. Then we output the contents of a and b again, and notice that a is now 2 and b is now 1. So in effect, it swapped those two ints. Below that, we create two doubles, x and y, and we assign the values 1.1 and 2.2 respectively. Again, we output the contents of x and y, and it shows 1.1 and 2.2, and we call swap again. Notice here I did not pass in double in the angle braces. That is because it knows implicitly that x and y are both double, therefore it knows to use the swap double version. So then it actually swaps those x and y values, and we get 2.2 and 1.1 now. One thing you might be wondering is whether or not this is performed at compile time or at runtime. Actually, when you compile your code, everywhere that swap is used, it will create in the background a function specific to the data type that you're using it with. So for instance, we have created two swap functions because one was of type int and one was of type double. It may be called something like swap backtick, the key next to the 1 on your keyboard where the tilde is. So it'll be called swap tick 1 for the int version, and then maybe swap tick 2 for the double version. And those are compiled in your code, and you can see them if you were to use the IL disassembler. A generic class is very similar to a generic method. So just as types are passed to generic methods, the types are used in the declaration of generic classes, compiled later on. Inside this stack class, just like we would represent a stack of coins, we are saying we have a list of items of type T. Since we don't know what they are to begin with, because it has not been defined yet, we just have to assume anywhere we wish to access this M items list, we have to refer to it as a list of type T. We have a function in here, or a property called count, which simply returns the number of items in the list. Then we have a function called push, which allows us to push an element of type T to the end of that list. Then we create a function which returns a value of type T called pop. And assuming that there are values in the list, we get the last value in the list using the item's last extension method. And then we store in a value of type T, and we return that item and remove the item out of the list. So if we were to look at the left-hand example where we create a myStack of type int, that means everywhere you see the red T, you would replace that with an int. Now, this particular code might make a little more sense because everywhere there's a T, there's an int. And just like the methods that we made generic before, this is done at compile time. So the compiler will actually create a version of myStack that accepts ints. Now, the nice thing about generic classes like this is it allows us to keep everything type safe. That way, when we create, let's say, a list of ints, we know the only thing we can store inside of that list is an int. We don't have to worry about being able to store a string in there. So in this case, when we create the stack of type ints, the only thing we can store within this stack are integers. And then once you create it, just like we used the generic list before, this behaves very similarly. We could again also create a myStack of type doubles. Then the compiler will create a specific version of this class that contains doubles. Now, you will never know what the actual name of the class that is generated by the compiler, as it's not necessary. According to you, it's simply a class called myStack of ints. When you define a generic class, you can apply restrictions to the kinds of types that client code can use for type arguments when it instantiates your class. The constraint is typically a requirement that the type be polymorphically compatible with the constraint type. You can also require that the types have a parameterless constructor. Now what this means is it allows you to say that your particular generic class can only use objects of a given type. So if we had, for instance, a base class called person, and we have a couple derivatives, one called student, one called employee, one called teacher, then what we can do is constrain our class, our generic class, to be of type person. Therefore, the only thing we can stick in this particular type of generic class would be a person, student, teacher, employee, etc. And again, as mentioned, we can force that the implementer of this particular generic has to also have a default constructor, in other words, a constructor that accepts no parameters. So if a client code tries to instantiate your class by using a type that is not allowed by a constraint, the result is a compile time error. Constraints are defined using the where statement. So here are some of the constraints you can use. You can say that a type is constrained to a struct, which means it must be a value type except nullable. Doesn't literally mean it has to be a struct, but things like int, double, etc. It just can't be of the nullable struct type. Where T is of type class, the type argument must be a reference type of any type. Where T colon new parentheses, this is the one that enforces a constructor that is default must be present in the implementer. Where T colon base class name, that says that the item must be of a specific base class type. We discussed this with the person, student, employee, teacher example in the previous slide. Where T is of type interface name, basically the same thing as above, except we're forcing it to be of a specific interface type. And then we have where T is of type U. Now this one's kind of interesting because you specify possibly two types in the generic where you're saying that the first type must be of type second type. So it allows you to pass in two different types to the definition of your generic, and you can force the first type to have to be of that second type. You can look up at that link at Microsoft.com for more information about this topic. And a simple example at the bottom shows our MyStack class again, but this time we are putting a constraint on T that it must be a reference type and have a default constructor. And just as we discussed before, it doesn't have to be a T, it's whatever legal name you wish to use.